Swayam Prabha. Digital India. Educated India.
Alright, so let's go back to some graph theory, right. So I will just, right, so now we are going to forget about the original phrasings of the question, right. So there was this question about the city of Prussia, then we wrote it in another language which was just drawing the graph without lifting the chalk, and then finally we wrote down in the language of graph theory, right. So, so in the language of graph theory, right, so what's a graph? Is just a set of vertices. You can think of this as a set of points, but the point is you don't need to actually draw it, right. I can just define a graph here, right. For example, can we have some silence please? Yeah. For example, we could define a graph here, right. We are all vertices and let's say hopefully all of you are friends, or maybe some of you know each other, but some of you don't know each other because you are from different schools, right. So maybe you haven't yet talked to each other, you don't know yet each other. So then you put an edge between two people if you already know each other, otherwise you don't put an edge, right. So that's what a graph is. It's a set of vertices and a set of edges, and each edge is nothing but a pair of vertices, right. For example, the pair could be me and you, for instance, right. Maybe we know each other, right. So that's what a graph is, and the point I want you to appreciate is you don't need to draw it. Of course, it's nice to draw it, but there is no really, graph doesn't have to be drawn to exist, right. And what is the question we are asking? The question we are asking, the original question is, does the given graph have an Euler walk? Right, so we'll just name it after Euler because Euler is the one who came up with it, right. So what's a walk? A walk is just, think about walking on the graph. It's exactly what you would imagine. You start at some vertex and then you walk along the edges of the graph to reach other vertices, right. And you do this in any sequence. That's what a walk is, right. So the only property a walk needs to have is for every edge in the sequence, the vertex that appears before it and the vertex that appears after it, they are the two ends of the walk. Yeah. Shall we write down some walk here? For in this graph, which is the original Koinsberg graph, I just redrew it. You can call the bridges B0, B1, B2, B3, B4, B5, B6. I can write down a walk here. For example, I can start at L3. Then I can walk here, B0, and I will reach L1. Maybe I will walk again. In a walk, there is no restriction. Walk is just any sequence that is valid. So I will walk on this again. Observe that I am repeating a bridge or an edge. I reach again L3. Now I decide to walk on this bridge, B3. Now I reach this vertex L2. Now I can decide to walk on this bridge, edge B5. I reach L4. This is a walk, right? This is just a walk. Of course, we are not interested in any walk. Every graph is a walk. I can just stay at the vertex. This is also a walk. I don't have to take any edges. I will just stay here. That is called walking, right? But what we are interested in is an Euler walk. So what is the Euler property? Each edge of the graph appears exactly once. This is the Euler property, right? So I want a walk in which every edge is there exactly once. That just means that in the original city, I can take a tour which will travel each bridge exactly once. Make sense? Okay. So that is what we call an Euler walk. Is the definition of an Euler walk clear? Yeah? Okay. So which of these graphs has an Euler walk? G0 or G5? Or neither of them? Neither. Neither G0 nor G5 has an Euler walk. Yeah? But we had other graphs. We had this graph that you can draw like this, and this is an Euler walk. Yeah? And we had another graph, very nice graph. And I got stuck. I can't do much. I wanted to draw this, but I couldn't do it the way I did it. But there is a way to do it, right? So this one has an Euler walk. Both of these have an Euler walk, whereas these do not have an Euler walk. Of course, just writing it doesn't make it true, right? I haven't convinced you, but looks like you all have convinced yourself for these examples. How you did that, I don't know, but you did it, right? So are you all convinced that these graphs do not have an Euler walk and these two have an Euler walk? So the general question is, if I give you an arbitrary graph, right, let's say 10 vertices or 20 vertices, and I just ask you, does it have an Euler walk? How do you answer this question, right? And if you have already figured it out, great. If you have read about it before or heard about it before, that's also great. But let's try to think we don't know. Let's try to pretend that we don't really know the answer to this question, and let's see how we would go about it. Yeah. So how would you convince someone that this graph, G5, does not have an Euler walk? How would you convince your friend, your neighbor, that this graph G5 or the original graph G0, Koinsberg graph, how would you convince someone that this doesn't have an Euler walk? Why exactly do you get stuck? Right, you try to walk, but then you realize that you are not able to convert your walk into an Euler walk. Right, so what exactly is getting you stuck? What's the reason you're getting stuck? Does it have to do with the degree of a vertex? Right, except that we never define degree. So the point is we need more terminology, right? So let's discuss a few more terms. So adjacency versus incidence. So you will encounter these terms in mathematics all the time, whether you are studying geometry, whether you are studying subjects like matrices, algebra, maybe not as much, or in graph theory, you will always encounter these terms. So let's just talk about what these mean in graph theory. Let me just ask you, right? So for most terms, I don't like to write down a definition. I just want to ask you, let me just label STUVWX. Can someone tell me what are the vertices adjacent with the vertex T? Adjacent to T. V, W and X. You all agree? You all get adjacency? Okay. So for two vertices, we will say whether they are adjacent or whether they are not adjacent. For example, S and U. Are they adjacent or non-adjacent? Non-adjacent, right? Not adjacent. What about U and V? Non-adjacent. What about T and X? Adjacent. Good. Alright. So we know what adjacency means for two vertices. So we have discussed adjacency for vertex. We can also talk about adjacency for edges and edges. Okay, let's do that. So the edges TX and SV. TX and SV. Are they adjacent? They are not adjacent. What about TX and UX? Adjacent. Yeah? Yeah. Two edges are adjacent if they have a common vertex. What about the edges B1 and B2? Sorry? You tell me. When are two vertices adjacent? Supposing my vertices are S and T. When will you call them adjacent?
When there's like no other vertex.
Think about edges. So let's look at this example. S and T, are they adjacent or are they not adjacent? Not adjacent. Why? There is no edge joining them. There is no edge joining them. What about S and X? Adjacent. What about U and T? Not adjacent. Yeah? Okay? Sorry? T and X, you tell me? Yeah, they are. There is an edge joining them, so they are adjacent. Right? So I will not write down. I will just ask you and make sure that we all are on the same page. Yeah? So we all agree? We all agree with vertex, vertex? What about two edges? Either they have a common end or they don't. They may even have two common ends because we are allowing this kind of stuff. B1 and B2 have two common ends, L1 and L2. So they are adjacent. Yeah? So we all agree with edge adjacency? Edge, edge. Observe that we were talking about two objects of the same type, either two vertices or two edges. If you say a line is, supposing you think about line segments and points, what would the word you use be? Are a line and a point adjacent or is the line incident at the point? Incidence. Incidence is generally used when you have two objects of different types. Okay? So for vertex and edge, we will use incidence. Yeah? For example, the vertex W. What are the edges incident at that vertex? WS, WT and WU. Is that correct? Yeah, I did not give labels to the edges. I am just referring to the edges using their ends. I can do that in this example because I don't have this kind of situation. Here I can't do that. Here I have to say B1 and B2. Both of them have the same ends, L1 and L2. Right? So sometimes it is helpful to give labels to the edges. Sometimes we won't give labels to the edges. Right? Okay. So for vertex and edge, we will use incidence. A vertex and edge are incident if the picture looks like this. Yeah. No, we will consider them different. So B1 and B2 are different edges. They just happen to have the same ends. Right? Especially in the Euler's problem, this was important because the two bridges were actually different bridges. So therefore, Euler could not have considered to be the same bridge. Yeah, we converted bridges to edges, right? Yeah. Sorry? You tell me, what would you like to say? B1 and B2. Do you think they should be adjacent or not? Yeah, we'll call them adjacent. Yeah. Both are same. They are actually called parallel edges. So if you want another term for this, B1 and B2 are also called parallel edges. I mean, we are using words from geometry, but we don't mean the same thing, right? They have other meanings. So they are called parallel edges. I don't really need this word, so I did not want to talk about it. But since you asked it, I mentioned it. Yeah. So because they have the same ends, we will call them parallel edges. Yeah. Okay. Are the terms clear? So now let's talk about the degree of a vertex. Quite a few of you have been using this word degree, right? So what do you think is the degree of a vertex? It is a number of edges incident at that vertex. Yeah? Okay. So let's write down this one. This is important. The degree of a vertex is the number of edges incident at the vertex V. Yeah? For instance, let's write down the degrees of the vertices for these graphs that we have drawn. 3, 3, yeah, okay. What about here? Most of them are 3. Are there any 2 degree? U is 2, V is 2, everybody else is 3. Yeah? Alright. And let's do these 2. What are the degrees here? The bottom is 2, top 3. And what about here? Everybody 4. Yeah? 4. Okay? So this is the degree of a vertex. Yeah? And so why do we think degree is important? Right? So let's go back to the drawing the graph without lifting the chalk version. Right? This is actually one of the most visual ways of thinking about the problem. Can you draw the graph? You have to start at some vertex. Right? Now we are going to specify things. You have to start at some vertex. You may end at any other vertex. But you have to draw the entire graph without lifting the chalk. Now think about whether this has anything to do with the degree of a vertex. Right? Take some time and think about whether this has anything to do with the degree of a vertex. And if you think it has something to do with the degree, write it down in your notebook. What does it have to do with the degree? And try to come up with an explanation. Right? So I'll come and walk around and try to give me an explanation of, right? And you may try experimenting on your neighbor. Right? So don't just come up with a guess, but also try to come up with an explanation behind your thinking. The question is the ability to draw the graph without lifting the chalk. Sorry? Yeah, Euler walk. The existence of an Euler walk. Right? Does it have anything to do with the degree of vertices? And if it does, what is it and why is it? Yeah? Okay? Yeah? No? Okay. I thought you were looking at me.
We both know. I found out last lecture.
Okay, fine, that's okay. You can still try to explain to somebody else, right? Articulating your thoughts.
The number of vertices that have an odd degree has to be exactly either 0 or 2.
Okay, okay.
Because for us to do a walk, we have to go into the vertex and come out. And that makes a graph. Except for the starting and the ending, which you either only go in or only go out, so only 2 of them are allowed to have one.
Yeah.
But then when you start in the same place, none of them are allowed. So only then an Euler goes.
Okay, thank you. Yeah.
The sum of the degree of vertices, like if you take this group, it should be equal to the sum of the adjacent group of degree of vertices.
Okay. Okay.
Will that?
But what are the groups?
No. So, like for example, if you take this one, the first one we did, here we have 2, 3, 2, and these are not adjacent to each other. So, the sum of these degree of vertices will be equal to the sum of their adjacent ones.
But that so that means that you are considering that your graph's vertices can be broken into 2 sets,
Yeah.
right? but I don't know if that is actually given to us. You seem to be assuming something about the graph in terms of the vertex being vertex set having two parts.
But the adjacent ones are not adjacent.
But that's not very clear, right? For example, if I give you, what if I give you this graph? So I'll put 6 vertices, okay, and put all possible edges, but don't put one edge. Now, what are adjacent ones and non-adjacent ones?
Yeah, it becomes ugly.
Right? So you're going too much by the drawing of that particular graph. But remember that I could have drawn it anyway. So try to remove it from the drawing. Basically, yeah. Okay. Cool. Yeah.
I had one idea. See, all these updates, but the number of edges should not be more than the number of vertices for any particular vertex. Because if that happens,
Number of edges should not be more than.
total number. For example, in the case of genome,
Yeah.
the number of we have 5 edges connected all to it. Now, when you take when we have to only trace one path that saturates or that removes all the edges. If one vertex is connected to a large number of edges, it actually creates a concentration at a point, so we won't be able to have one connection.
For example, can you draw G0? It's okay. No, draw it again. My earlier drawing was very ugly. This is nicer. 1 second, please. So now what I'll do is, I will draw one more edge. Now think about this graph. Yeah? Think about this graph. Yes.
So the non-adjacent vertices must have like the same number of degree of vertigo. Does that make sense?
Can you repeat it? The non-adjacent?
So the non-adjacent vertices
Yeah.
must have like the same number of degree, same degree as that.
So if two vertices are non-adjacent, let's say x and y.
They should have it's the same degree.
I see.
It works for these graphs.
Right. Yeah. But see if you can contradict that. See if you can make a small example where that is false, but the statement is still true. Let's see if you can do that. Yeah. So let's think about the question again, right? So I want you to go back to the model of being able to draw the graph without lifting the chalk, right? So let's say I'm able to draw the graph without lifting the chalk. So there are two possibilities. Either my chalk ends at the same point or it ends at another point. Yeah? Okay. So I'm drawing the graph starting from some point, some vertex, and I draw everything, and I either end at the same vertex or I end at a different vertex. So this could be one situation, start and end. And another possibility is that I start at some point, some vertex, and I end at the same point. Do you all agree? These are the two possibilities. Can we think about these two examples? Can we think about these two examples? Which one is in which category? First one starts and ends at different points. And the second one, no matter where you start, you will end at the same point. You all agree? Okay. So what I want you to think about is, let's not worry about these two cases. Think about some arbitrary vertex. Think about some third vertex, right? Some other vertex. And here also, think about some other vertex. Liberate yourself from the two cases. Yeah? Just think about another vertex. Right? At some point, I may visit this vertex. I may reach this vertex while I am drawing, right? I may reach this vertex at some point, but when I reach this vertex, I do that using a vertex or an edge. I do that using an edge. So I reach this vertex, but this is not the start or the end. Even here, this is not the start or the end. So what must happen? I am not done yet, right? Because this is not the start or the end. So I have to leave. Do you all agree? If I reach this vertex using my chalk, using an edge, I also have to leave this vertex because it is not the starting or the ending vertex. Yeah? Okay? So if I reach it, I have to leave it. If this is the only time I reach this vertex and I leave it, what is the degree of this vertex? 2. If this is the only time I reach this point in my drawing, the degree is 2. Maybe I reach this point again, because remember, repeating vertices is allowed, right? In particular, if this vertex has 3 edges, you can see I will have to come back here at some point in life because I need to draw the whole graph, right? So when I come back to this vertex, if I do that using some edge. But now I must leave. What's going on? If I arrive, I must leave, right? Unlike Hotel California where you can't leave once you're there, here you arrive, you have to leave, right? So what does this tell you? The degree of this vertex is? The degree of this fellow is even. You all agree? The degree of this fellow is even. Yeah? And this fellow is any fellow in both the drawings. Same here, right? Do you agree that there is no distinction between these two for other vertices, right? So I leave. If I arrive again, I leave. The degree of any other vertex must be even. You all agree? Yeah? Now the only thing we need to think about is the starting and the ending. And there are 2 cases, right? So now think about the 2 cases. What about this? Think about this case first. Think about this case. Is this really different from this? Is this fellow really different from this fellow? Think about drawing the graph without lifting the chalk. You come back here. Could you have started anywhere else? Or must you start at this vertex and end at this vertex? Think about it. Think about this graph. Can you make an Euler walk on this graph? So it will start and end at some vertex. Can it be any vertex or does it have to be a specific vertex? If you have an Euler walk that starts and ends at the same vertex, observe that you could have done that anywhere. You could have gone to any other vertex and traced the same thing in the similar way and you will be able to draw the whole graph. Do you see that? There is no difference between this fellow and this fellow in this situation. Here there is a difference actually. Right? Let's just not even draw a graph. Let's just draw something where I start at this point and I will end at this point. Okay? I'm not allowed to lift the chalk. So let me use some color. Yeah? Is that okay? Instead of starting here, could I have started here? Yeah. Right? Instead of starting here at this pink point, I could have. Yes, that's exactly the point I'm trying to drive home here, right? So it doesn't matter. In this case, it doesn't matter. However, the other case doesn't look like this. The other case, you are starting and ending at different points. Can you start anywhere? You don't even need a graph to think about this, right? You just draw some weird stuff, right? Here the starting and ending are really different from the other points. Whereas here, starting, ending is just, all of it is just your imagination. There is no real start or end. So therefore, by the same argument, what is the degree of this vertex? It is even, right? So this fellow is also even, this fellow is also even. Now the only thing that remains is this situation. You start somewhere and you end somewhere else. Now you can analyze on your own. Can you just do the same analysis? How did we conclude this is even? Can you now think about these two vertices? Now the start and end are different. What can you say about the degrees of these vertices? Odd, you all agree? You start, you may never arrive, you may never return again because you don't need to return. If you return, then you must leave because the end is different. If you return, you must leave. If you return again, you must leave. So what you get is, this fellow is odd and that fellow is also odd because the start and the end, if I can start here and end here, I can also start here and end here, right? That is clear, right? Yeah. So what you get here is odd and odd. So in order to have an Euler tour in the graph, you either need every vertex to have even degree, or you need at the very least two vertices of odd degree, everybody else is even. Do you all agree? What we have done so far, we have just listed down what are called necessary conditions. These are necessary for an Euler walk to exist. Do you all agree? Let's just write it down. I don't need this. I can erase this mess. Necessary conditions for the existence of an Euler walk in a graph G. Yeah, what's necessary? It's necessary that either every vertex has even degree, or exactly two vertices have odd degree. Either each vertex, sorry, I'm lazy, this is vertex. Either each vertex has even degree, or there are precisely two vertices of odd degree. In fact, if you go back to our analysis, for this case, it actually means that start is equal to end, the first case. And the second case, start is not equal to end. You all agree? So in fact, this case is the start equal to end case, and this second case is the start not equal to end case, right? The original problem of Koinsberg did not actually say that you have to come back to the same point or say the same landmass. Sorry? One odd. Make a graph with only one vertex of odd degree. Okay?
So you go this
What are the degrees? 1
1 and 2.
1 and
1 and 2.
1,
degree. 1, 3, 2. How many odd? There is no graph with only one vertex of odd degree. Okay, I did not prove it. You have to prove it. Right? So, Here is what I call, my lectures always have DIYs, do it yourself. So here is a fact, don't look it up, try to prove it yourself, try to convince yourself why this is true. The number of odd degree vertices in any graph is always an even number. The number of odd degree vertices in any graph is actually a very fun problem. You can state this in a party. If you go to a party and you want to kill it, here is one way to do it. Ask everybody how many hands they shook, right? So maybe some people meet at the party, they shake hands or they don't shake hands. But whenever you shake hands, you have to keep track of how many, right? You're super nerdy. So you're going to count how many hands you shook, right? At the end of the party, the host, who is also equally or more nerdy than you, is going to ask you how many hands you shook, right? And the number of people who shake hands with an odd number of people, that number has to be an even number. Because of this version, this is called the handshaking lemma. What I just wrote down here is generally called the handshaking lemma. Right? So, anyways, I don't want to go into handshaking lemma. You can think about it yourself and convince yourself why is this number an even number, right? And if you think hard enough, you will see a very nice reason why it is an even number. No, I don't want to answer it. You think about it later. Yeah. Okay.
If you have an edge that connects a vertex to itself, then does that count as one edge?
2. Yeah. Contribution is 2. I don't want to get into that because I did not consider that case. Yeah. Were there any other questions or concerns? Okay. So coming back to this point, what we have so far is just necessary conditions. This is not actually saying that whenever these conditions hold, it does not actually say that there is an Euler walk in the graph. Do you all agree? We haven't proved anything. We have just observed that for an Euler walk to exist, one of these conditions must hold, right? We haven't said that if these conditions hold, then there is an Euler walk. Yeah? Do you see the distinction? Okay. But let's go back to the Koinsberg graph. What can you say about the Koinsberg graph using this? What are the degrees? All vertices of odd degree. And there are 4 vertices of odd degree. Right? So it is not this case. It is also not this case. Therefore, this graph does not have an Euler tour. Yeah? Similarly, what about this graph? It also does not have an Euler tour. Okay. But what we have discussed does not actually say that this graph has an Euler tour. Right? It just says that those graphs don't have an Euler tour. Right? We still need to show, if we believe that the opposite is also true, whenever these conditions hold, then there is an Euler tour. Do we believe that? Do you all believe this statement? That if every vertex has even degree, or all vertices except 2 have even degree, do you actually think there is an Euler tour? Is it true that if these conditions hold, then there is an Euler tour? Is the question clear? How many of you think this is true? Okay, you can. Right, okay, yeah. So that's exactly the point we'll have to go. Right, so if you are saying yes, that is because you are assuming something else about the graph. For example, you were thinking that this is 2 graphs. But hey, maybe this is just 1 graph. Why can't this be 1 graph? All of this could be 1 graph. No? What's the problem? Sorry? Which graph? Right. But I'm now taking all of this as 1 graph. Is there a problem? Is there something in the definition of graphs that says that this cannot be a graph? No problem, right? Do you agree? What is a graph? A graph is just set of vertices and set of edges. You all agree? Graph is just set of vertices, set of edges. Every edge is a pair of two vertices. Basically it's a pair of vertices. So why can't this be a graph? Maybe this is my graph. This is one graph. G. Why not? Could be one graph, no? And what about this fellow? This could be one graph. H. This is more interesting. Which condition does it satisfy? 1 or 2? It satisfies the second condition. H. H satisfies the second condition. Does it have an Euler walk? Does H, this whole graph, 5 vertices plus 6, 11 vertices, does it have an Euler tour? No, right? How will you draw this graph without lifting the chalk? Once you finish this, you will have to lift the chalk and come here. Yeah? Right? So, we need one more condition, which we have been assuming all along, because I made drawings that were convenient. Right? So, we are assuming that we are not somehow allowing this kind of stuff. Or we want our graphs to satisfy some property, which will get rid of this possibility. So, what is that possibility? Was somebody use the word connected? Right? Did somebody use the word connected at some point? What was that? What's connected? Right, so you see a difference between this graph and the original graph, just this one. Right, there is some difference between them, right? What's that? I will give you a hint. You can use the word walk. Can you use the word walk? Okay, I'm not able to follow some of the meanings like interconnected. I don't know what it means. So I'm trying to, but yeah, maybe you're on the right track. Yeah, okay. Walk that saturates the entire world graph. I don't know what saturates means. All the vertices can be touched by a walk. Okay, fine. This is okay. You want all the vertices to be included in a walk. Is that right? Can I make it simpler? Can I just say something about any two vertices? For any two vertices U and V, can you now complete it? There is a walk that starts at U and ends at V. Remember, we defined walk before we went to Euler walk. Walk is just the first condition. So for any two vertices U and V, I should be able to find a walk. There should exist a walk that starts at U and ends at V. This is true in this graph. In this graph, this is true. Right? This was what? This was something. What was it? Something G7, I don't know. In G7, it is true. If you take any two vertices U and V, there is a walk that starts here and ends here. Yeah? But if you consider the whole graph H, is it true? For example, if I take X here and Y here, there is no walk from X to Y. Sorry? You mean inside the same part? Then it works, but I want this condition for any two vertices. So that is what we will call a connected graph. Okay? So we will say that a graph is connected if for any two vertices there is a walk that starts here and ends here. Okay? Do you all agree that for Euler tour to exist, for Euler walk to exist, we need the graph to be connected? Yeah? Okay. Sorry? That is also necessary. Good. So that is also a necessary condition. For an Euler walk to exist, we need the graph to be connected. Right? Otherwise, we will not get the Euler property. Each edge appears exactly once. There is one minor issue we need one more condition, and G is connected. There is one small issue here. I'm getting into super technical methods, right? So with math, the details are very important. Any kind of false statement is not acceptable. Let me ask you a trick question. I actually claim this is not necessary. I actually claim that this is not necessary. Can someone make an example? We need something weaker. I claim that this is not necessary. It's really a trick question. You're going to hate me once you hear the answer. Sorry? That is connected. That just means connected. My point is, actually we don't need this. We need something slightly weaker. I want you to give me example. I don't want to give example. I mean, I know example. Right? Yes. Yes. Throw a vertex that has no edges. Now this is my graph. How many vertices? 1, 2, 3, 4, 5, 6. I added a new vertex Z. Okay? This is just a vertex with no edges. Does this graph have an Euler walk? Yes or no? Do you all agree? Yes? It has an Euler walk. Euler walk doesn't say every vertex has to appear. Right? So actually this is okay. But this is annoying. Single vertex with no edges. Right? So I can make it more precise. I can say that it has at most one connected piece that has an edge. Now this is a piece that has no edges. So I will throw it away. Right? We can do that. But instead of doing that, what I will do is, I will assume our graphs are connected, because clearly this is really annoying. Okay? So I'm just going to think of connected graphs, and I'm going to ignore this possibility. Single vertices without any edges. I'm just going to not allow that. Is that okay? Okay. Fine. So now let's write down a statement. Sorry? Euler walk. No Euler walk. Yeah. G and H are disconnected. They don't have Euler walk. Yeah. Okay. So let me write down a statement. So remember, the original question was, does a graph have an Euler walk? I'm going to change the original question. I'm going to make it, does a connected graph, does a given connected graph have an Euler walk? Okay. So now I'm assuming my graph is connected, because I don't want to deal with that possibility of single vertex with no edges, right? That's really annoying. I don't want to deal with it. Okay. The question I've changed, I'm asking whether a connected graph is an Euler walk. Okay. And what we know is, what we have proved so far, proved or observed, if a connected graph G has an Euler walk, then the number of vertices of odd degree is how many? 0 or 2. Then number of vertices of odd degree is either 0 or 2. Do you all agree? If a connected graph, actually that is true for any graph, right? If a graph has an Euler walk, it must have the number of odd degree vertices either has to be 0 or 2. It can't be anything else. Whenever you see a statement like this in life, or at least in math, what's a natural question to ask? It's an if-then statement. What would you ask? Is the converse true? Is it if and only if? Like, that's what we really love in mathematics. We like if and only if statements. Two things are the same. So that's the question we're going to ask. Is the converse true? If I tell you that, hey, here is a connected graph with this property, does it actually mean it has an Euler walk? Right? So that's what we'll ask next. And is the converse true? Right? So now what do you think? Is the converse true? What's your guess? Would it be possible to get some water? I ran out of water. Can I get some water, please? Is there a place I can fill? Sorry. Yeah, thank you. So how much more time do I have, or am I done? $12:20. So I should basically conclude. Is that right? 5 minutes? Okay, I'll conclude in 5 minutes. Oh, then I did not need water. I had lost track of time. Sorry. Okay, sure. I'll try to finish in 5 minutes. Right? So this is the. So I want you all to think about this. Right? So this is actually indeed true. Like, I'll already tell you that this is true. How do you prove such a statement? Right? Mathematics cannot just be, yes, I feel this is true, therefore it is true. Like, nothing in life should be like that, right? You should be able to read fake news and hopefully tell that it is fake news, right? So, is it actually true or not? Of course, good news in mathematics is that telling whether something is fake news or not is much easier, unlike the real world, right? So, so the answer is indeed yes. Here is a fun fact. Euler actually said in his notebook that the converse is true, but Euler did not give a proof. Now we don't know whether Euler had a proof, right? But Euler actually never gave a proof that the converse is true. It was other mathematicians who proved that the converse is true, right? So how would you prove such a statement? Proof by contradiction. Okay, but how? Right? Okay, so you can, so yes, you can try by contradiction. And in fact, there is a way to prove by contradiction, but it's more sophisticated, but that's okay. Right? So, let me ask you, what about induction? Have you all seen induction? Is induction something the high school curriculum teaches or not? Yeah, it does. So, would you be able to prove such a statement by induction? Why not? So, the converse would say that if every vertex, if the number of odd degree vertices is 0 or 2, then the graph has an Euler tour. What's the problem? Why can't we prove the statement by induction? Is there a fundamental reason why you cannot prove this by induction? Ah, right. N and n plus 1. Nah, so that's the thing. What is n and n plus 1? Right? So that's the issue with the high school examples of induction. High school examples of induction are basically sum of the first n natural numbers is n times n plus 1 by 2. Standard example, right? Prove by induction. The thing to induct on is very clear. You induct on n. You're trying to prove a statement about natural numbers. So you induct on n, you assume it is true for a smaller number, and then you show that it is also true for the bigger number, right? But induction is actually much more general than what you see. And that is what I want to just say, that induction is not about n and n plus 1. Induction is, you want to prove something about certain mathematical objects. You have a class of mathematical objects. In high school, the induction examples are basically natural numbers. You're trying to prove a statement about natural numbers. 1, 2, 3, 4 and so on. Right? But in general, you may have some set of mathematical objects. Here the objects are graphs. Thank you very much. Right? You have some set of mathematical objects that could be natural numbers, but it could be something else like graphs. You want to prove by induction. The main point about induction is you should try to not think of the base case. If you tie yourself too much with the base case, you won't appreciate induction. Think about an induction step. You have a large mathematical object. You want to prove that it has an Euler tour. In this case, it is a graph. You have a connected graph where every vertex has even degree, or there are two vertices of odd degree. You want to prove there is no Euler tour. The principle behind induction is to get a smaller mathematical object with the same property. Can you remove some things from the graph, get a smaller graph with the same property? Then by induction, that graph has an Euler tour, because that's how induction works. And now you have to show that the bigger graph also has an Euler tour. That's basically the main principle behind induction. You have a big mathematical object. It may not be natural numbers. In natural numbers, it's very easy. You go from n to n minus 1, or you go from n plus 1 to n. But in general, your mathematical objects may be more complicated. Can you remove something systematically and get a smaller mathematical object? Then the statement is true there, and you have to show that it is also true for the bigger graph. And of course, the question is, when you can't remove anything, that's your base case. Right? The natural number 1. You can't subtract anything to get a natural number, assuming you are defining natural numbers to start from 1. Some people start from 0, right? So that becomes the base case of your induction. Okay? So what I would like you all to think about is, how would you prove the converse using induction? And it's pretty non-trivial. At this point, your exposure to graph theory would be rather limited. But just think about it. Can you, for example, from this graph, can you remove something to get a smaller graph with the same property? Actually, we can do this example. Can you remove something from this graph? Can you remove something from this graph? The middle triangle. Let's remove the middle triangle. I removed 3 edges. Do you agree that this is a connected graph where every vertex is even degree? Aha. This is the induction step. And I will conclude here. I'll let you think about it more. Yeah? Okay? Thank you. Sorry? These vertices? No. There are edges incident at them. So you can't remove them. No. The problem is, if you remove the vertices, so you can think more about it. But the point is, we want an Euler tour. Observe that if you take any Euler tour here, you can actually include these 3 edges and get an Euler tour for the bigger graph. That is not so clear if you remove vertices. So in this particular case, in this particular problem, the idea is actually to remove some edges. And why edges and what kind of edges, I will let you think about it. Right? So the example that people suggested, remove these 3. I could have also removed the outer 3. There is no difference between the inner 3 and the outer 3. That would also work. So what do you have to remove, and why does it work, and when does it not work? That is your base case. Right? So there is some work to be done here. Yeah? Okay? Any other questions, concerns? Feel free to ask anything. It doesn't have to be related to graph theory or anything. If there's anything else you want to ask, I'm happy to answer those questions as well. Yeah. Sorry? How did I learn to be ambidextrous? So during my PhD, I'm basically left-handed. Of course, this is controversial because when we generally say left or right, we mean writing. Whereas actually we should talk about eating food, which is a much more fundamental activity. But anyways, we generally talk about writing, right? So I am actually left-handed. On paper, I can only write with left hand. I cannot actually write with right hand on paper. I mean, I can, but it's really bad. You don't want to read it. And during my PhD, I had some issue with my left hand. There was some numbness or something. So I decided to give my left hand some rest. And then one day I was in one of the rooms and I used to write a lot on boards, as you can see, right? And I just decided to give my right hand a try. I don't even remember consciously making this decision. And it just happened. Like I was just able to write. Right? And the difference is, it's not a horizontal surface, it's a vertical surface. And the margin of error is much greater. So if any of you want to try, you can try writing with your other hand on the board. And you never know, you might actually be able to. Or with some practice. Yeah. Thank you. Any other questions? Okay, if not, I'm still going to be outside. If you want to ask anything, feel free to just catch me in the next 5 minutes and I'm happy to discuss. Thank you. Yeah. Can I write with both hands? So recently I went to Gujarat, which happens to be my home state, and I was giving a talk at IIT Gandhinagar, I think, and a similar thing happened. They were asking me, can you write with both hands? So I tried and I failed. I mean, I was able to, but I made a mess. It was not what I wanted to. So my brain really struggles to actually do the coordination simultaneously. Yeah, but yeah, thank you.
So, vote of thanks. On behalf of the entire RSIC team, it is my privilege to thank Professor Nisha Kothari for his amazing lecture on graph theory. You showed us how the problem we all did as 8-year-olds, drawing a graph without lifting our hands up, was us doing a Euler work. Your way of teaching us, by asking us to think on our own in between the lectures, by breaking the problem into simpler steps, you do it yourself, and most importantly, your ambidextrous abilities all amazed us. I'm sure all of us learned a little bit about graph theory and perhaps a little less scared about mathematical terminology today. Thank you, sir.